So on one level, the first step of this problem is pretty straightforward. Even if you have no idea what the shit any of this is, there's the formula. And we all know how the hell to do this by now. If you just cover that, you realize what you have to create. What does O represent? Observed. Expected. Anybody figure out what goes in this column here?
Isn't the percentage, isn't it all like 20%? Because one at the bottom add up to 100? Or am I like...
Yeah, how many total observations, how many total things are we talking about? No, how many total things or how many total observations did we make? 100. And if we expect it to be uniformly distributed, each one of these have to get 20. Right? 100 divided by 5.
20, 20, 20, 20, 20.
Okay.
Is that why you're being nice?
That's part of the reason. Yeah, I'm nice on a few levels. I made it nice to divide. Even if it's not nice to divide, just freaking do it in the calculator. Create L2 and make it, if this was 107, you would make each one of these 107 divided by 5, right? And it's going to put all the decimals in. It won't show them, but they'll be there. Just do it in your list. That kicks so much ass. So this would be list 1. This will be list 2. This would be list 1 minus list 2 all squared, right? But again, this is a nice one to do by just outside of the calculator. It's pretty straightforward. 3 squared, are you guys with me? It would actually be negative 3. Who gives a shit? Because I'm going to square it, right? So this would be 9. Somebody with me? Observed minus expected, and then square it. Why do we square it? For a very similar reason to why we square, not the exact same reason to be honest, but back when we did standard deviation, we had to square so it would add up to 0. In this case, any deviation from what was expected counts against me. So I don't want them to be opposite signs. They should all add up against me. So that's why one reason why we square.
2 squared is 4. 4 squared is 16.
1 squared is 1. 4 squared is 16. And then we talked about why I might divide by the expected. I want a relative kind of idea of how far off that is. So relative to what I expected, how far off was I squared-wise? It would be 9 out of 20, which is... what do you get? 0.45. 4 out of 20. 0.2. 16 out of 20. 0.8. Right? 1 out of 20. 0.05. Why? Okay. So what's that add up to be? Is it 2.35? 2.3? I don't know. 2.3? Yes? Okay. All right, let me stop for a minute. So I really want this to make, obviously. I always want everything I say to make sense. If my expectation had perfectly met our observations, all of this would be 0, right? Any direction I'm off by, since we squared, will count against me, meaning gets further away from 0. So the whole idea, visually, this one, we remember, this is sort of like chi-squared star. She sells, about a she-show. Okay. Tongue twister, chi-square star. And it's going to normally have a shape sort of like this. Right? There's some homework about when does it become more normal and so forth that you got to read a little bit. Oh, no. 0 would mean your observations perfectly lined up with your expectations. If my observations perfectly lined up with my expectations, would that be evidence that it doesn't match what I expected? Let me say that again. If this was exactly what I expected, is that evidence that it does not line up with my expectations? Nope. Would it be evidence that the population that I took this from perfectly lines up with my expectations? No! This is just a freaking sample. This is a sample taken from some population. So by just the same way, can you ever show evidence in favor of the null hypothesis? Can you ever prove the null hypothesis is true using a sample? You guys remember this? And you're all like, dude, we're past that shit. Can we just leave it? No. Does anyone remember the point of this? The null hypothesis. Do we ever accept it? Do we ever accept what that crazy old dude's saying? No, no. Even if the sample shows the sample mean exactly what the claim was, right? The claim is the mean is 9, and we get a sample mean of 9. Does that prove that the population mean is 9? No, it's just a sample. There's going to be variability, right? Does it prove it isn't 9? Obviously not. Baby, so I really need you with me here. Even if this had lined up perfectly, all we could say is that would not be evidence that it doesn't meet expectations. Of course it wouldn't be. Okay. So, 0 means these are perfectly the same. So not only do I need to get away from 0 to show evidence that it actually doesn't match expectations, I've got to get far enough away from 0 to account for the regular variability I expect in a sample. Any sample I take is going to have variability in it. This is exactly the same idea as the null being the dude who thinks it is in here, and the alternate being I think it's away from there. So if I get in here, I don't care if it's really far away from here, that's still where I expect it to be, within the sample variability. It's got to be far enough away from what was expected. Now be very happy that I did not make these problems into a full-blown hypothesis test. Oh my God. Okay. How do I look up the rejection region chi-square? We have our chi-square star, right? You can call it that if you want to. I need to know the rejection region. So 2 things. Did I say what alpha was? So what do we assume it to be? 0.05. So alpha is 0.05. What's the degrees of freedom? Is it 99? What's the degrees of freedom? 4. Good. Number of categories? -1. So degrees of freedom is 4. Can you look up on your chi-square chart? So let me show you. If you just got that chi-square chart, I'm not sure if it's daunting or what. Maybe? I don't know. Let's try this again. Did you try turning it off and turning it back on, Jeff? Yes. Does this work? No, that doesn't even work. Okay. Let me see. Okay, you guys don't see this. I have to tell you this really quickly. Do y'all understand? Old man technology, exciting part of class. In front of my face, right now, what just happened? I hit the on button, it's been on. Right now, it flipped itself to off by itself. I love it. Sorry, just had to share that. Let me push the on button again. See what it does. All right, well, so on the chart, degrees of freedom are right here. Okay. So that's the computer. Let's see if the document camera works. Well, that doesn't quite work. Let's turn this off. Turn it back on. All right, I'm going to give up on it. So, just like the t-score chart, degrees of freedom, what sucks is this chart is quite a bit different than what we're used to. On the z-score chart, when you look up a z-score, what area does it tell you? Where's that area when you look up a z-score? It's to the left, correct? This one is to the
Right.
right. So when you look up a z-score chart, it tells you the area below the z-score you looked up. So to the left. This one is all about to the right. We want there to be 5% in this tail. That would be a 5% chance of getting a sample in here when it really is supposed to be no difference, which is very low, so therefore we would say it's more likely that there really is a difference. So if you look up degrees of freedom 4, 0.05, what do you guys get?
9.488.
I mean, look at yeah, 9.488. Did you guys see that? So I would need a chi-square score above 9.488 in order to say that this is wrong, that it's not uniform. We only made it up to 2.3. Nowhere near far enough away. And you know, on a surface level, that matched up pretty close, right? There really wasn't that far off, but we know by now not to go only by that. We could very easily be wrong based on what we just observed. We don't have an intuitive sense of what far enough away is in any given situation. Okay. Maybe.
So you said you need a score, a chi-score of 9.488 to prove that it's not uniform.
Yeah, chi-score's got to be
Chi-score.
above this, just like the rejection region and hypothesis test that we did before. We have to get a sample that's out here. If we do that, that's so damn far away from where it would mean it lines up perfectly that it's evidence that it doesn't line up at all. That it doesn't follow what we expected it to follow. Okay, maybe not. So again, if these were perfectly the same, if what I expected to see was what I actually saw, that would be here on the picture. Are you with me? If O and E were the same all the way down, what these all be zeros? O minus E would be 0 everywhere, correct? O minus E squared divided by E would still be 0. Yes? So then we would be here. The minute I'm not at 0, that means my sample had some variability in it. Every sample is going to have some variability in it. So not only do I have to be away from 0, I have to be away from 0 enough for the sample to show evidence that the whole population doesn't follow this. Did we just prove that it's uniform, that the population is uniform? I love you guys so much. You're like, I don't know what you want to say. No, hell, shit, no. We can't prove shit. Are you kidding me? We just haven't shown evidence that it is uniform. We haven't shown evidence, well, in this case, that it isn't uniform. We didn't show evidence that it's not uniform. I don't like it. So when we find somebody not guilty, have we proven that they're innocent?
No.
Shit, no. Hell no. Right? Which is one reason why we say not guilty instead of innocent. It sounds like semantics, but it actually, there's a reason behind that. Yeah.
So if we get a number like the x squared thing in the thing, then it would be uniform, right?
Yeah,
We prove
chi
that it
squared.
is,
We got here.
right?
So is that enough evidence to say that it did not, that the population is not uniform? No, that's not enough evidence to say it's not uniform. It's too close to what it would look like if it was uniform. So let me try this again. If I had a population of people, 28,000 people, right? And the ages were actually uniformly distributed. Are you with me? So if I have 28,000 people, let's do this. Let me give you some concrete numbers. No, don't break his glasses. Stop. If I have 28,000 people, so I got 28,000 people. And let's say it is uniformly distributed across these age groups. Can somebody figure out how many people would be in each age group? How many people would be in each age group? Same exact way we just did it a minute ago, right? You got 28,000 people. You want to divvy them up evenly amongst 5 categories.
5,000.
Yeah, 5,600, right? That is what it would look like if I had a population that was truly uniformly distributed across whatever the categories were. You with me? My categories could be anything, by the way. It could have been hair color. Right? My categories don't have to be quantitative. They're just categories. Okay. If I take a sample of 100 people from this population, can you see how it would be very easy to not get a sample that is uniformly distributed? Do you guys see that? So in this case, I am showing you behind the scenes what we normally don't know. I am telling you, the population that I got this sample from is uniformly distributed. It is. If I take 100 people at random from all these people, do you think that each category has to have the exact same number of people in it? Of course not. We're randomly picking. Would it be impossible for me to get 100 people just that were 20 to 30 years old? Would that be impossible? Would that be unlikely? Shit, yes. Okay, so it is uniformly distributed. Is my sample uniformly distributed? Was my sample uniformly distributed? Shit, no, which is exactly what I would expect. There's going to be variation in any sample I pick. That's why when we look for evidence that it does not follow what we expected, it's not enough to just go, oh yeah, it's not what I expected. No, this is exactly what I would expect. I just don't know if it's far off enough to say, oh yeah, the whole population must not be. Maybe. So that's why it's not good enough to stop here and go, okay, those are different. No, I got to actually see how different. Is it different enough to account for all the variability that's possible, right? So that when we do the rejection region, when we get the chi-square for the rejection region, right? That is saying we think that anything below 9.488, this whole area is acceptable sample variability. Anything past that, we go, okay, that's gone past what we would expect for variability. That's evidence that it actually is not uniform. Are you guys?
Pass that to the right.
Yes, this is the rejection region. If 0 means it perfectly lines up, and of course it does, because then the differences would all be 0, right? If it perfectly lined up, all of these would be 0. My chi-square would have been 0. We would have been right there. That would not have been evidence that it's not uniform, because then my sample itself would have been uniform. That can't possibly be evidence that it's not uniform. So I've got to not only be different, I've got to be different enough. I've got to get past all of the possible sample variability.
Do we want to be in the rejection region?
It depends. I don't know. Real quick. If your claim, if this is us, and we're like, we really think this is true, and if it wasn't true, I would have a really bad day. It would suck, because my stuff is due tomorrow. I'm like, okay, let me double check to make sure my theory is correct. Are you with me? You with me? So if this is us, so if we expect this to be uniform because it matches the theory, and my freaking thesis is due tomorrow, and I've got to stand up in front of these people and show them the shit, I'm like, oh shit. So we are like, please, dear God, please don't let me disprove this. Are you with me? So yes, any situation, depending on if you're the one making the claim. Now, normally in science, we don't give a shit. We actually are like, if it disproves my claim, that's exciting. If it's evidence for my claim, that's exciting. Every damn thing we do is exciting in science. We're like, but that's weird. I don't know if you guys are, maybe. But again, in certain situations, you can have, like, oh, I really hope this is good, because then the rest of my work looks good and I can keep going. Okay.
So, by it being 2.3, we're saying it's uniform because it's not in the rejection region.
All right, you ready?
No.
I cannot prove that a population is uniform just by taking a sample.
So then what
So
are
real
we
quick,
doing?
real quick. Huh?
Then what are we doing? It's a sample that we're testing.
If somebody is a suspect in a murder case, and there are things that line up, right? They had the ability, they had a motive, they had all these things, but we just can't show enough evidence. Does that mean that they're innocent? Does that mean that they're innocent if the result is a not guilty verdict? Does that mean that they're actually innocent?
No.
Good. You with me? Because we just weren't able to show enough evidence. So, is it possible that the population actually looks like this, for example? Oh, there's a good marker. And I don't know what the last one have to be, but oh well, something. Is it possible that it looks like that? And that we took a sample that looked like this? Is that possible? Yes. So, I really, are you with me? If the population actually looks like that, if that is what the population looks like, couldn't we get a sample of 100 things that look like this? Is that possible? Yes. So if I don't get here, we get to here, that cannot mean that it's evidence that the population is uniform. I cannot show evidence the population is uniform. I can only show evidence against it being uniform.
So that's the point of this, is going against the uniform.
Yes, that's the point of any hypothesis test. We can never show evidence that it equals something. We can only show evidence that it doesn't. So, I can't show evidence that the entire population would have a zero difference. I can't. But I can show evidence that it looks like it would. If I get out here, that would be strong enough evidence to say it looks like it's not uniform. It's so far away from a uniform distribution the sample is that the population seems to be most likely not uniform.
When you were Jedi mind tricking me, you just said that a sample can't tell you that.
The sample cannot tell us that it's uniform. A sample can all day long tell us that it looks like it's not uniform. There's a difference, right? So, most trials cannot tell us that the person's actually innocent, for sure, right? But it sure can tell us if it looks like they're not innocent. Can you accumulate enough evidence to say, oh yeah, that guy probably did it? Okay, but there's no way in hell that you can actually prove. No, I got to be careful. Some trials maybe, but most trials, they exist because we don't know. We want somebody to look at the available evidence and figure out which way does it seem like it goes, right? But I can't prove somebody's innocent. If there's not enough evidence, does that mean maybe somebody missed something? Correct? Maybe the prosecutors suck. We've seen that shit. We've seen prosecutors sucking in real time. You guys, well, I don't know if you guys watch any of this stuff. There's been some trials recently. All right. You guys with me a little bit? Okay. All right. Maybe. So again, this is a old idea from when we did hypothesis testing. A sample should, if it's a nice random sample, it should mimic properties of the population. But of course there's going to be variability. Yes? So any test we do, it's always, being different is not good enough. But everybody agree that this is definitely different from this. There's no question, they're different. But it's not different enough to overcome the fact that it's just a sample. It's going to have variability, right? If the average age of Grossman is 27 and I pick 100 people, could I get an average age of 23? Yes. Could that be evidence that the average age is not 27? Yeah. Is it evidence the average age of all Grossman students is 23? Shit, no. It's just a sample. Maybe?
Yeah.
How's everybody else doing? Are you guys? Okay. All right. How does everybody feel about just reading this chart? You guys feel pretty good about that? Okay. So let's do this. I want to talk a little bit about section, what was it, 11.6. And then I'm going to kind of like start doing a review for the final a little early. We'll start today. So 11.6, so remember my lecture from last Wednesday, if you were here, or if you watched the video. I tried to show the analogy between all the different possible z-score formulas. All right, little dude, put you to sleep. Lay down. Turn you off, even though you never really turned on. Okay. So this is the formula we just used for chi-squared. But just like with z-scores, there's multiple formulas that all relate to the same shape. So this is one of them. And then the other one is that first one we actually talked about was this guy. What was it, Jeff? Oh, yeah. So this one is actually a lot closer to a standard z-score formula because it's, what's a z-score formula fundamentally do? Like if the mean was 11 and I have a data point of 40. Just by me telling you that, is that enough to know if that's close? If 11 and 40 are close? Of course, what am I missing to know if they're close? Standard deviation. Standard deviation gives you an idea of distance in statistics, right? So 11 and 40, they could be as far away as, or they could be right next to each other. So if the standard deviation was 20, without doing any work, not really any work, roughly how far apart are those?
2 steps.
How many steps?
2 steps.
2 steps, roughly. Right? A little less than 2 steps,
Yeah.
right? So the z-score formula directly compares a value we get from data, 40, and the actual average of all the data, right? So here it would be z equals 40 minus 11 divided by 20. So we'll get whatever the shit that is, okay? This formula does a very similar thing. It takes a value that we get from data, right? The S would come from a sample we take. It compares it to the actual population number, but it does so through division instead of through subtraction. Okay. There's a lot more behind this formula than we obviously, number one, have time to get into, and number two, our math background probably doesn't contain what we would need for that kind of discussion. So a lot of what we're doing is built on calculus. I'm not going to suddenly teach you calculus, so if you're freaked out. All right. Okay. So, really quickly, let me do this. Let me see if I can. Do you remember, to create a confidence interval, we had to go back to the backwards formula for z-scores? I don't know if you guys remember this. We had to actually start with this. So a real quick summation of the lecture from that is, if we don't have mu, we use x bar. If we use x bar, we must have taken a sample, and then of course the z-score, and then plus or minus to go up and down so many. Okay, so that was the really rough, quick lecture from that time. But do you see how we had to solve this for what we don't know and kind of go from there? So here, if I want to create a confidence interval for a standard deviation, we solve this for, so how am I, well, all we have to do is this, you ready? We kind of solve for this, so we get sigma squared equals n minus 1 s squared over chi squared. Let me stop for a second. So here's how this works. If I have my distribution, and let's say I want to make 90% confidence interval, right? And I talked about this a little bit the first day. This shape is not symmetric. It doesn't have negative values.
What was it was x bar plus or minus, and I didn't get the rest of it.
Oh, that's just the old. This is just from before, right?
Okay.
Yeah, this is the confidence interval.
No
That's nothing new.
Okay. Cool.
That's just me making a connection. Yeah. It's not symmetric. So confidence intervals for means kick a lot of ass because if I wanted 90% confidence, I would go down 1.645 and up 1.645 steps. Yes? Because it's symmetric. It's around 0. It's symmetric. It's going to be equidistant. It's going to whatever one is, if the other one's the positive or the negative of it, right? We're not going to get all that niceness from here, too bad. So can somebody tell me, for example, what's the area here? Careful. There's 90% in there. How many tails did I just make? Whenever I make a confidence interval, I make 2 tails. So what percentage is up here? 0.05. Yeah, 5%. 0.05. Let's say that I take a sample of, what do you got, Jeff? 91 things. I think that's on there, right? I forget how far up this goes. Yes, okay, good. Say I take a sample of 91 things. So this is not a goodness of fit test. Does everybody agree? We saw our first example where degrees of freedom is not equal to n minus 1. Goodness of fit tests are based on the number of categories. That's what rules the day for goodness of fit tests. This is not a goodness of fit test. I'm trying to make a confidence interval. So now degrees of freedom goes back to what it used to be. So what's the degrees of freedom for this? 90. 0.05 in this tail, degrees of freedom is 90. What would the chi-square up here be? This is what I call a chi-square big. Because it's the bigger one. It's crazy. Everybody got their chart? You guys looking it up?
113.145? I don't know.
I'm with you. Yeah, there you go. Right, so you look at 0.05, go down to 90 degrees of freedom, you get 113.145. What about this one? Chi-square small. So what percentage is to the right of it? Because that's what this thing is built off of. What percentage is to the right of this?
95.
95%. So look at 0.95. And again, shoot. I love that nothing technology-wise is working. What's kind of cool is, let me see if I can show you guys. Do you see how you had to look at the second row in? Do you see there's a middle where it makes a big jump from 0.90 to 0.10, right? So you had to look 1, 2 over for 0.05, correct? Notice how you have to look 1, 2 back for 0.95, yes? So it's really symmetric on the paper at least, right? I don't know if you guys are understanding, but it's really kind of simple. If I look 1, 2 over for this, I got to look 1, 2 back for the other side. So what chi-square do you get for that?
Would be 69.12.
Where are we at? Sorry?
Was that 90 degrees of freedom?
90 degrees of freedom, 0.95, right?
0.95 was 69.126.
Yeah, 69.126. You guys see that? Okay. Let me know if you're not able to get those numbers. Okay. So here's how this works. Because it's not symmetric, it looks a little bit worse. Basically what I'm going to do is this. I'm going to say, look at this. So if I know S, so if I take a sample of size 91, I can totally calculate S from my sample. Once I get my sample, I can calculate S. And let's say we get 11.14. Okay. I can get an estimate for what sigma is by plugging in both of these into that equation one at a time. So here's what the confidence interval looks like. Sigma squared is going to be between So if I put the bigger chi-square into this formula, isn't that going to make this the smallest it could be? If I divide by the biggest chi-square it could be, wouldn't that make the output the smallest it could be? If I divide by the biggest number I can, won't my output be the smallest it could be? If I divide by the smallest number I can, won't my answer be the biggest it could be? That's why I always hate it when some books call this chi-square left and chi-square right, which kind of makes sense until you plug it in and then left and right are in the wrong place. I prefer chi-square small and chi-square. If I divide by small, I get bigger. If I divide by big, I get smaller. Bam. So this definitely is not symmetric, so I couldn't write it like we could x bar plus or minus z sigma over square root of n. So this shit right here is like this. But I have to write it like this because it's not symmetric. I can't, this error is not going to be the same on either side. So let's see what we get. What's n minus 1? 90. So we get 90 times 11.14 squared divided by chi-square big. And then I get 90 times 11.14 squared divided by chi-square small. And then you get whatever the hell that is. So now it's just a bunch of plug and shove. So let me know when you think you have this. See if I can do it a little bit in my head. No, I don't want to. I think it's going to come out to be like 90 point something, isn't it? Can you guys get that? Anybody?
How did you get the 11.13?
Oh, it was given to us. And that's why I said right here, if I take a sample, I could get the standard deviation, and I said, let's pretend like we got.
Oh, okay, you just.
Yeah, it's got to be something I'm given. Just like a z-score problem, I got to be told the mean and the standard deviation, right?
Is that supposed to be squared?
Or that S.
Yeah.
What do you mean?
Yeah.
Yeah.
That's hilarious, Jeff. Squared. Sorry.
I was like, I
Sorry.
don't know.
Don't raise
what
it to
hell
the
that
standard
is.
deviation
Yeah, I
power.
was
That's
like,
weird. Sorry. So notice you get the same number on top for both sides, right? All right, let me see. Yeah, okay. So it's around 90. Somebody think they got this one? It's around 90 something? Almost
98.
98 point.
7-1.
714 roughly, right?
Okay. I was like tripping. Yes,
Okay,
yes,
Let me
yes.
put this up here.
Thing.
So we get
My fault. Let me put you.
98.714 roughly. So the variance is between 98.714 and what do you get up here?
161.574.
161.574. Alright. So we see that? Is that alright? Now I want to know standard deviation, what this shit's going on. That's the variance. Everybody agree with me? Sigma squared variance. I want to know stuff about the standard deviation, so what do I do to everything? How do I make this into just standard deviation? What do I do? How do I get rid of the square? What do I do?
Root it.
Square root. So go ahead and square root both sides. Square root that sucker. You'll get like 9.91. I don't know. Making shit up. What is it? 9.93. Okay. Well, don't look at. I mean, it's almost 100, so I knew it was almost 10. A little less than 10. I just made shit up. I got close. 9.93. And then this will be like, what is that, 12.78. It's probably 12.8 something. Was it? 12.71? All right, it's pretty good. So, our sample estimate was 11.14. So that's the confidence interval for where the real population standard deviation is. It feels exactly the same thing as what we do with this kind of confidence interval, right? We get a point estimate, and then we go from here to here. We think that captures the real mean. So from here to here, we are 90% confident that this interval catches the real standard deviation of the whole population. Maybe. Can somebody tell me really quickly, is 11.14 right in the middle of these two? How do you check? There we go. Somebody's doing something. So how far away is it from this side? It looks to be 1.21 away. And how far away is it from this side? Looks to be about 1.57 away, is that right? Now please, dear God, so with a normal confidence interval, does everybody agree that if I have the mean in the middle, I go up and down the exact same amount, correct? That's the error. It's the same number, up and down the exact same amount. Here, if I start at my point estimate and go down 1.21, but then here I got to go up 1.57. Why is it not symmetric? Because the stupid picture's not symmetric. I didn't have to say anything. I just said, you're like, well, that basically summarizes the whole damn semester, Jeff. Thank you. But I really want you to understand, since the picture's not symmetric, our interval's not going to be symmetric. This interval was symmetric because the freaking normal distribution is symmetric. So, okay, maybe. All right. Now, one reason that's all I'm going to say about that is because I'm going to make 11.6 extra credit. But I wanted to spew that at you before I said that, so you maybe pay more attention than if I didn't. Everybody with me? 11.6, I believe that's the section, let me double check. That should be the section where they ask you to make confidence intervals. Shit, Jeff. Let me see.
Oh man.
Thought I had this open.
Right when I started making sense. Making sense. He's like, oh, it's all extra credit.
Well, if it makes sense, then do it. You get extra credit.
I know, man. I need to.
Let's see.
Some things make sense.
Very infrequently do I ever apologize for making sense. Let me see. Yeah, there we go. Oh, I think 11.6 is even... Ooh, 11.6 is even worse. Ooh. It's hypothesis tests. So be really happy I'm not making you do 11.7 or 11.6. Yeah, I like it. I think they also include... Oh, I'm not going to worry about it. So 11.6, either way, 11.6 is extra credit. So let's do this. Everybody has a practice final, correct? So what just happened, by the way, is I just talked about the last new idea we're going to talk about this semester. That's what just happened, right? And you're all like, oh, I can only cram so much in my little brain, Joe. I understand. I'm with you on that. So let's do this. Let's go ahead and construct the formula sheet. So one thing you could do is you could just bring all your formula sheets, right? But there are a few recently that you need to add. I'm just going to do it from the beginning, just because I notice it sometimes spurs conversation. Where you're like, oh yeah, what the shit was that? Okay. You seem to be working. So, if you go all the way back, one thing that's not going to show up, and I am going to hold to my promise, you're not going to have to do standard deviation formulas from chapter 2. Right, we're going to do one var stats if I want to figure out what the standard deviation is for a set of data. Are you with me? So basically almost all of chapter 2 let me think. All the formulas that you're not supposed to memorize, the only one that's going to show up is the z-score formula. It's going to show up in a minute. So then we start with really chapter 3, good old probability stuff. What does that mean again? Given. I like it. Alright, so that's chapter 3 stuff. Remember, don't forget this. There was really only one problem where we had to use the formulas, and that's when I tell you, like, probability of A is 0.7 and the probability of A given B is 0.35, blah blah blah. You know, then you have to plug those numbers into the formulas. If I give you a contingency table, just a chart with numbers in it, right? I've got people with a master's degree, people without a master's degree, and then I have amounts of money at the top. Then you can answer all the probability questions without ever using any of this shit. You just use the basic idea of probability, right? What is the basic idea of probability? The probability of anything in the universe is something over something. So if I want to know, I got a big hat and it's got all kinds of different colored chips in it, and I want to probably pick a green chip. What do you have to know? 2 things. You only have to know 2 things. How many green chips?
How many total?
And how many total? So what's the idea of any freaking probability anywhere in the universe? The number of things that match what I'm looking for divided by the total number of things. That's what every single one of these stupid formulas actually means. Just in very detailed situations. All right, so these look worse than what I just said. You guys agree? You're like, yes, Jeff. Those look a lot worse than what you just said. Just like any math teacher, damn it. But we did probability problems and created these formulas based on what the shit we did. You guys remember that? We didn't know these. We created them after we did shit. We're like, well, we did this. So you only have to use these if I don't give you an ability to count all the different situations. If I just tell you, probability of B is 0.47, and probability of A and B is 0.6, and just like that one problem, I think I had a problem like that on the double quiz and so forth. Okay, so that's chapter 3. Move on, Jeff. Okay. Chapter 4 was this business, right, where we introduced probability distributions. Let's see, there it is. Bless you. You almost gave yourself enough room, Jeff. Right? General probability distributions. Now, real quick, this always happens. 2 ways this happens. People use the wrong formula for this kind of problem. If I give you an x and a p of x, it should make immediate sense that you want to use one of these formulas because they're the ones that have x and p of x in them, right? But people try to use binomial formulas when asked questions about this and so no, you use x, p of x formulas for that. The next thing that was in chapter 4 was the binomial stuff, so let me put these up here because I don't have enough room for that. And then you got this one. Alright, so that's chapter 4 stuff. That's a mu dude.
What is the last right there? Oh, it was a Q?
This poor little guy?
Yeah.
That's
no.
what my-
No. Up there where it says standard deviation equals the... It's a Q, I got it.
This guy?
Yeah.
Yeah, it's also a Q. Yeah. Yep. Math is my first language, so. And the right response would be, well, that's math, Jeff. Be quiet. So chapter 4. Chapter 5 was uniform distributions. No formulas to write down. If I give you a uniform distribution, what's two things I want to see on a picture? If I say draw the uniform distribution, two things I want to see. What was that?
I don't know. Bell curve?
It's not a triangle. No, uniform.
Oh, I thought you said
What shape is a uniform? Rectangle. Could be a square,
Oh.
but it's a rectangle, right? So I want to see the rectangle, right, with the labels, and then what I want to see here?
The fraction.
The height.
The height.
If I'm missing either of those things, you're going to lose half credit or whatever. Okay. So I got to see the picture with the, from 11 to 8 or whatever. From 11 to 8. Good job. 11 to 18. If it was from 11 to 18, what would the height be? 11 to 18. How tall would it be? 1 over 7. Because that makes the whole area 1, which matches up with all the probabilities adding up to be 1. Okay, I like it. So chapter 5, not a damn thing you can put down. Sorry, I didn't mean to be so. Okay. Chapter 6 was the whole damn class, basically, right? Once you learned chapter 6, we just went insane with this shit. And chapter 6 was all about z-score chart, backwards z-score formula. I think. Was there something else in chapter 6? No. Then chapter 7 was where we did central limit theorem. So you'd have this, and you'd have this, right? Let's also put down these. Well, let's see. I want to make sure you guys get this on your formula sheet, right? It's the same thing except with S's. It's all the same shit except with S's. So what would, if I have S, what would this be? If I only know S, not sigma, what score do I use? Z or T? Alright, you probably can't see that over there, can you? I'll put it up here. So I've got, let me see, I'm gonna move this too. Alright, so down here I've got S x bar, S over square root of n, then T would be x bar minus the mu divided by S x bar. It's exactly the same formula, just if I don't know sigma, I use S, and if I only know S, I can't use Z, I've got to use T. So if you want to, you can even put a little star next to it, because that kind of lines up with hypothesis tests, right? That's chapter 7, kind of melding into chapter 10, right? Chapter 8 is all the confidence interval stuff. So you've got interval for the mean. You got 2 of these, of course, lining up with what I just said. Z with sigma, T with S, right? Yes?
Will you be curving the final?
I don't know.
Okay.
Yeah, until I finish grading something, I don't know if I'm going to curve it or not. Depends.
Gotcha.
A better question is, would you be open to curving the final, Jeff?
Are you?
Yeah, I was
Yes.
going to say, what's the answer?
Final is the most often thing I must curve, so we'll see. That doesn't mean everybody does poorly in the final. You guys can kick ass on the final.
Possible.
Right? So we got 3 of these, and again, our means are the ones that have the option between Z and T. Now be really careful. It's not good enough to say, I'm going to use Z-scores because I got percentages, and we always use Z-score. No. What do you check to make sure that a percentage problem is normal? It's got to be normal before you use a Z-score. What's the check? NP and NQ have to be greater than equal to 5. I love it. Right? Just like N greater than 30 for these, NP hat, NQ hat for this. Okay. And then, of course, we had, oh man, I love this classroom. It's not really set up to use the board, which is kind of strange. Then we have these formulas for N. That's an S. kind of glad it decided to do the review over 2 days. Yes? Sorry? Sorry. What happened?
I'm still on this.
Am I for? So that's chapter 8. This and this together are chapter 8. Chapter 9 is where we did hypothesis tests. The only new thing that chapter 9 gave, and again, if you want to, you could rewrite this shit over here so it's all together. But the only thing that chapter 10 added that we didn't know before was this guy. Right? And we stole the standard deviation, we stole it from here. So let me ask you this. When do I have to use S? When do I have to use S if I don't know sigma? So when do I have to use P hat? When I don't know P. In a hypothesis test, the whole assumption is that we know what P is. We're assuming we know it's from the claim. It's whatever the claim number is. And we're trying to see if that leads to a contradiction. That's why those don't have hats on them. They're the unhatted ones, right? Okay. We did a lot. Holy shit. I'm not done. So that's chapter 9. If you want to put the chapter 10 formula down, that was the extra credit from section 10.2, right? That was the x bar 1 minus x bar 2. Put that down. You didn't have it. And then we have chapter 12. There's nothing to write down because it's all just, do you remember how to do it in the calculator and then interpret what you see? And chapter 11, of course, is where we have this guy. Right, and you can put the other one down there. If, well, you can put the confidence interval down if you think you're going to try that out. I might put a problem like that on the final, on the bonus section, right? So the bonus section, I'll definitely have at least one problem that is just bonus from any section, and then I'll have a couple problems that are from some of the extra credit sections. Okay. That's a lot. Mm-hmm. Okay. So, do you want, let's see, what time is it? We have a choice to make. We could try like number 11 right now on the practice final, or number 5. That's the more recent stuff, right? The chi-squared problem is number 11. The correlation problem is number 5. Or you could call it a day and then devote all of Wednesday to review. I'm cool either way. I don't know how you feel. What's up? You want to do number... All right, here we go. We're going to do number 11. Now, at any point, if you want to leave, you don't have to be here. This is college. So if you want to leave, you can leave. And this is going to be on the answer key eventually anyway. But if you want to try number 11, let's go ahead and try that. All right, so we're going to try number 11 on the practice final. We'll do that, and then we'll call it a day. Of course, I can't project anything. Oh, thank you. Let me try this one more time, because I never learn.
Do you have any more copies of the practice test?
Oh, yeah.
Sure. Okay.
Oh, thank you. So seeing how my... Ooh, which one's that? Is it going to work? You're going to work now, aren't you? You piece of technology. Okay. No, you're not going to work. Okay. What could be wrong with you? Let me see. Is it just that? This is really loose. It is just that. I love it. That's funny. Okay. I'll be okay. So we're looking at number 11. So this is the kind, it doesn't say uniformly distributed. So how do I figure out what to put down for expectations? Yes.
Multiply the total by the percentage given.
Yeah, so let's figure out what the total is first. So let's put our observed down. Oh, it does say 342. So here's a beautiful example of using the calculator to worry about all the freaking decimals. If I do 13% of 342, is that going to be a nice whole number? No, it's not. So let's do this. Let's all try the calculator. So go to Stat Edit. Let's put data in. I'm going to clear some things. I'm going to need several. Jeff, good job. I'm going to need several lists. I'm going to clear several lists. Okay, how's that look? So clear out your first 4 lists at least, right? So in L1, I'm going to put our observations. So let's see, what do we have? We have 53 A's. Keep going. This is, what do you guys think about this? What kind of distribution does that look like it's trying to mimic? Normal. So this is kind of like when you have 5 categories, this is an approximation for a normal distribution. These are the percentages I would expect across 5 categories. Obviously, if it was 6 categories, it would change a bit. Does that make sense? So, but this is what it looks like for 5 categories. So to figure out the expected, we do exactly like Ryan said. We would take, for example, I expect 13%, so 0.13 times 342, and we let the calculator worry about all the decimals, right? So let me do it again. So I'm going to do 0.13, 13% of 342, shabam. Now, it shows 44.46, but it's actually got the entire decimal in memory now. So it's not rounding, which is kind of nice. Now just keep going. 0.2 times 342. Did you do it all right, Jeff? Maybe.
Wait, explain that one again. What did you just say?
So for example, this first one, I expect 13%, 0.13 of times 342.
Okay.
Yeah. What is expected value another name for? Expected value. What's that another name for? Mean, right? So is it okay that I'm expecting 44.46 people to have an A? Does that mean that I expect somebody to lose over half of themselves somewhere or something, right? 0.46 person. No. This is an average. It's an expectation. So it could be any number it wants to be. What am I going to make L3?
L1 times L1 minus L2.
Good. L1 minus L. So parenthesis L1 minus L2, close parenthesis squared. So that is O minus E squared. Enter. I mean, look at that. That kicks so much ass. And then L4. What's L4 going to be? Yeah, L3 over L2. Kick ass. L3 divided by L2. Shabam. Now, who remembers how to get our chi-square star quickly? Yeah, first I'm going to get out of here. I'm going to hit quit, second mode to quit. Then I'm going to go second step to get to list. I want to do math to a list. I want to sum up a list. I want to sum up list 4. Is everybody with me that wants to be?
Sum again on this.
Oh yeah, so go right off stat, it says list.
Mm-hmm.
Hit second stat to get to list. I want to do math to a list. And number 5, I want to sum up that list.
See what you got for L4.
Did you make it here, Ocean?
Yeah.
Okay, so do sum and then sum up second 4 to get L4. All your L's live above the corresponding numbers, right? So what is that? What the shit did I just do? What is that? What did I just calculate? Chi-square star, like, right? So this is our chi-square from our sample. What we get? 6.975. So we do this a little backwards. With a normal hypothesis test, I got to set up the rejection region. It doesn't really matter. So now, did I give us an alpha? So of course we assume it's 0.05. What's the degrees of freedom?
Yeah.
No, careful. This is a goodness of fit test, right? So how many categories? 5 categories, so there's 4 degrees of freedom. You're going to keep seeing this number because, I mean, 0.05 is the most commonly used one. We'll see. We saw this earlier today, I believe. What number do you guys get? So if you look up 4, 0.05. Yeah, 9488. There he is again.
You don't want us to be like doing the little graph things too?
Yes. Did we make it far enough away? So here's the rejection region. No. So can we reject that the grades followed the pattern? No. We have not found evidence that the population we got this from does not follow the pattern. I know some of you guys had really bad English teachers that might have taught you that double negatives are bad. We've moved past that shit, right? So some of you guys might be like, well, why do you say we have not found evidence to say that this does not follow the pattern? Why don't you just say it follows the pattern? We had the whole discussion earlier. I can't say that, right? So double negatives totally mean something. They have to exist. So does this group follow? Well, we have not found evidence that they don't. That doesn't mean they do, but it does mean what I saw didn't contradict it. You guys kind of with me? So it's sort of like the theory of evolution. Certain people like to pick on the word theory. Evolution is true. There is a theory of how it works. We have not seen any scientific evidence to go against the theory of evolution that requires a rewrite. Does that mean that our theory is true? No, we just haven't seen something to contradict it yet. This is how all of science works. Okay, that's totally enough. So even if you want to stay, don't. Get out of here. So I'll see you on Wednesday. I'll have the answer key for the practice final. I'll have the quizzes graded. I don't know. Somehow I'm going to do all that. Get any questions or anything, just come up and see me. Otherwise, I'll see you Wednesday. Don't forget whatever stuff I've got of yours.